There we go. That's better. Better for me anyway. All right. So we're going to introduce some new material today, and in your textbook it's chapter 16 on acids and bases. Let's see, take control and have control. There we go. We've done gases. We're going to get acids and bases, and then redox reactions will be the last one. We're not going to do energy. So don't let that panic you. Okay. What do we mean by acid and base? Everybody has a kind of a intuition about what acid is. Maybe not so much what a base is. But what do you think of when you think of an acid? I think of sour. Right? Anything that's acidic will be sour. And when I was going through chemistry, we used to taste stuff to see if it was sour. Of course, we don't do that anymore. It's probably not a good idea. But what is a base supposed to taste like? Anybody? Base is typically bitter. So if you take a medicine, most medications tend to be basic. So unless they're covered up with some type of flavoring, and you taste the medicine itself, it's going to be very bitter because most of them are basic. Some of them are acidic, but well, never mind. We'll move on. The other thing that you might think of term is corrosive. Strong acids and strong bases can be corrosive. That is, they can damage your skin. They can damage your mucous membranes if they're too strong. They can even damage metal pipes if they're strong. Everybody knows about Drano, right? Or liquid plumber. That's nothing more than sodium hydroxide in a thick solution. You pour down your drain. And what it does is most of what holds a plug in your drain is organic in some form. Lots of times it's hair. And the base, the sodium hydroxide, will catalyze the destruction of that material without damaging your pipes. Acids will do the same thing, but they'll damage your pipes. So, well, metal pipes. Now with plastic pipes, it doesn't matter. Anyway, okay. So, your book does not contain a discussion in this chapter on equilibrium. There's a whole chapter in your book on equilibrium, but it's not part of the course content outline. So I excerpted just some important information from that chapter. If you want to read the chapter on equilibrium, fine. But this should give you enough where you have a better understanding of how acids and bases work. So we're going to talk about equilibrium, extracted from chapter 17. So what do we mean by equilibrium? Well, in chemistry, equilibrium is a term that describes the macroscopic world. We think that all things are equal, nothing is changing. So an equilibrium situation will look like there is no change. But on the microscopic level, we know that there's furious activity. This is one example. evaporation and condensation. If you have a liquid in a container and you stopper it so that the gas is contained above the liquid, then initially there's none of the liquid in this space up here. It might just be air. It could be a vacuum. But initially, you're going to get evaporation. In other words, molecules from the liquid are going to leave the liquid phase and enter the gaseous phase. But you reach a point where you get a return condensation. So as soon as you start getting these gas molecules up here, there's a tendency for some of them to return to the liquid phase. So they do that at a furious pace. And at some point, the rate of evaporation equals the rate of condensation. And at that point, you have an equilibrium. Okay, that's just one type of equilibrium. This is a phase change equilibrium. So as long as you've got this stopper in the bottle, you can reach a state where evaporation and condensation are equal. Of course, as soon as you pull that stopper out, all bets are off, right? Because you can evaporate into this open space, and there's so much open space outside that eventually all the liquid will evaporate and none will return. So you need that enclosed environment to actually witness this equilibrium state. Now, chemical equilibrium refers to reactions. So if we have a situation where we have something reacting here and producing products, in the past, up to this point, we just had a single barbed arrow showing that reactants go to products. But in fact, as long as all of these reactants and products remain in the same environment, you will get a return reaction. C's and D's will have a tendency to return to A's and B's. Right? So this occurs at a certain rate, and this occurs at a certain rate. And this will initially, this will be at a fast rate, the forward. And the return reaction will be almost non-existent. But eventually, you'll reach a point where this reaction rate will equal that reaction rate. And at that point, you have an equilibrium. And we measure that equilibrium in terms of concentration, not in terms of absolute amounts. We talk about equilibrium in terms of concentration. So the concentration of C and D will increase to a certain point, and A and B will decrease until you reach a state where the forward reaction rate equals the return reaction. Now, one principle that is extremely useful in discussing equilibrium is what happens if you are in equilibrium with so much A and B, so much C and D, and they look like they're not changing. The concentrations have stabilized at a certain level. You're at what we call equilibrium. Then what happens if you change one of those concentrations artificially? You do something to disturb it. For instance, let's say
It's 10 after 8.
C, right?
10 after.
Question?
No, I'm sorry. It was my daughter.
Oh, okay. So if we do something to disturb this equilibrium, say we add some C to this side, then what's going to happen? Well, a French chemist from the 19th century said, this is exactly what's going to happen. When you disturb an equilibrium, the equilibrium is going to respond in such a way to reestablish the equilibrium. So if you increase the amount of something on this side, the equilibrium is going to shift to that side until it reestablishes a balance, until the equilibrium equilibrium is reestablished. That is Le Chatelier's principle. Okay, here's an example. Concrete example. So we have water and carbon monoxide, and that square is supposed to be a double barbed arrow. So you get water as a gas, reacting with carbon monoxide as a gas, and it's in equilibrium with the products, hydrogen gas and carbon dioxide gas. Okay? So let's say we have established equilibrium. Now we have so much of this on that side, so much on this side, and they don't have to be equal. You don't have to have equal concentrations on either side. Each reaction is different at a given temperature. A certain amount will be over here, a certain amount will be there. Sometimes you have large amounts of product and very small amounts of reactant, and vice versa. So that's not the issue. The issue is we've established equilibrium. Now what happens if you add more water? If you add water to that class, equilibrium is going to be shifted this way. Now, we're not going to use up all of that water that we put in there, the extra. We're just going to use up enough of it to reestablish our equilibrium. What happens if we add more hydrogen? Well, it's like the previous example. If we add more hydrogen, it's going to shift the reaction back to the left. Some of the hydrogen we added is still there. We just used up enough of it to reestablish that balance again. Now, we have a mathematical expression for this equilibrium, and it will be equal to a constant value. And for every reaction at a given temperature, that constant value is equal to this expression. So I'm going to use these as an example. Notice that here we have products on top, the reactants on the bottom, and the power of these square brackets, like that, they mean equilibrium concentration. So once the equilibrium is established, you have a concentration for each of the reactants and products. So what we would have for this one was, instead of C, we have hydrogen. Okay? And hydrogen has a coefficient of 1, so our power is 1. And the other reactant is carbon dioxide, and it also has a coefficient of 1, so it's to the power of 1. So the products are always in the numerator, and the reactants are always in the denominator. And all the coefficients are 1, so all the powers are 1. That is an equilibrium expression, and this is known as the equilibrium constant. That constant can have subscripts that help indicate what type of equilibrium it is. In general, you just put an EQ there for equilibrium constant. And that usually means that the reactants and products are expressed in terms of molarity. Okay, moles per liter. Other types of K values can be used. Later, when we talk about an acid equilibrium, we'll put a subscript of A for acid. Or if we're talking about a base, we might put a B for a base. So the subscript can give us some information about what type of constant we are describing. So here's another example. For this reaction, and again, that box is a double barbed arrow. For this reaction, which is one of my favorites, otherwise known as the Haber-Bosch process, we're combining nitrogen gas from the atmosphere with hydrogen gas and producing ammonia. And when it's balanced, the coefficients are 1, 3, and 2. So the K value then would be the concentration of ammonia to the second power divided by the concentration of nitrogen to the first power times the concentration of hydrogen gas to the third power. Okay, so that's an equilibrium expression for this equation. And as long as the temperature is constant, that value will be constant. If the temperature changes, then you will get a different K value. Okay. Now, I sort of alluded to this difference before. As long as the temperature is constant, these concentrations can be almost anything, as long as the expression, when you fit those values in here, you get that K value. And that means you're at equilibrium.
Yeah.
But so what that means is you can have different concentrations of ammonia, nitrogen, and hydrogen and still get the same K value because this is a ratio. But suppose we have a situation where you have extremely high values of ammonia, then you would have to have extremely high values of nitrogen to have a constant value here. So the concentrations, the absolute concentrations here, describe an equilibrium position. And the equilibrium position can be different, but the constant will always be fixed. So you could say we're at equilibrium and we want to add some more nitrogen. So we know from Le Chatelier's principle that the equilibrium is going to shift to the right. But it won't shift all the way. We would have, let's, for example, we start off with 1 molar nitrogen. And we add enough to give us 2 molar. Right? So then we're going to shift that way, but we're not going to use up all of this because the ratio determines how much is left over. So let's say, for argument's sake, we have, once the equilibrium is reestablished, we have 1.2 molar of nitrogen. Now we've got a new equilibrium position because the concentration is different than it was before. Right? So that's the difference between the equilibrium and the equilibrium position. The position can be have different concentrations, but we still have an equilibrium of nitrogen, hydrogen, and ammonia. Okay, any questions about that? All right. So we won't be here too much longer, and then we'll start talking about acids and bases. But I think the discussion of acids and bases will be much clearer after this material is introduced. And in fact, we're going to use an acid to describe an equilibrium expression. So remember when we started naming compounds? Right? We know what an acid is because it has a proton out here in front. This is the one that dissociates. Right? So if we put this in solution, what is it going to do? Some of those hydrogens are going to leave that solution and end up like that and leave behind the acetate ion. All right, so we have taken this acetic acid, put it in solution, and part of it dissociates into hydrogen ions and acetate ions. So this is an expression that can be described in terms of equilibrium. And we can write an equilibrium constant for that one. And since we're talking about an acid, I'm going to put an A down there instead. So how would we write this one? Well, let's make sure it's balanced first. One hydrogen here, one there, one acetate there, one acetate there. Okay, so we're good. All the coefficients are 1. So we would have this one, products first, on top. Right? And on the bottom, concentration of the undissociated acetic acid. So there's your equilibrium expression. That one times that one divided by this one is constant at a given temperature. Okay? Okay. So now, what about calculations? Well, I should make one point before we go on. If you haven't already thought of this, why don't I stick units of measure in there? Right? Well, we said most commonly we use molarity, right? So if you put molarity in there, what are you going to get out the other end? Well, with the last one, we're going to have molarity times molarity divided by molarity, right? Hydrogen ions, acetate ions, acetic acid. So this is going to be, the K value will be in terms, its units will be molarity. But what if we had, just for argument's sake, one of these was squared and one of them was cubed. So then what would you have? Well, this would be molarity times molarity squared, which would be molarity cubed, and they cancel out, and you have no units. Right? So the point I'm making is that with an equilibrium expression, you've got so many possible combinations. Powers can be introduced and generate an infinite number of units of measure for the K. So typically, and by convention, when K values are reported, units are not given. We just don't put the units in there. It'd be too big a mess in any reference manual to have units along with the K value. So what we have to do is be very careful about how we set up our K expression. And as long as you do it right, then the values, when you solve the problem, will come out correctly. Here's an example. Say we have N2O4 that is decomposing into 2 NO2s. Let's see. Oh, I see Josh. Let me mark him down before I forget. Don't see Brianna. I don't think, let's see. No, Brianna's not here. Okay. So in this expression, what would it, first of all, our equilibrium expression be? Well, K then would be this concentration to what power? Squared, right? Divided by this concentration to the first power. Okay? So now, if you're given the concentration of the reactant as this molarity and the product of that molarity, and these are at equilibrium. Right? Whenever you see the square bracket, that means you are at equilibrium. Then we would put 0.060 molar squared divided by 0.055. Okay, so you square this one and divide by that one, and you get 0.065. And notice, and we don't put any units there, because what would the units be? Well, it'd be molarity squared divided by molarity, so this would be molar if we were to put units there. Okay, so what else can we determine from the K value? Well, we can make some qualitative judgments. If the K value is extremely large, much larger than 1, what does that say about the equilibrium position of the reaction? It favors products, because products are in the numerator. So if products are in the numerator and the value is very large, that means this is large and this is small. Okay. Conversely, if the K value is much, much less than 1, very small, that means most at equilibrium, you're going to have a high concentration of reactant and a low concentration of product. Okay. So, if the K value is extremely large, we can say that the reaction goes virtually to completion. That is, most of this is consumed and gives you all product. That will give you a huge value. Now, what would that say? Of course, I hope you realize that these reactions can be written in the reverse direction. You can just flip them around and say, put this on this side and that on that side, right? But then you wouldn't have the same K value, would you? So if you flip the reaction, if this is a K value here, and you flip the reaction to this one, right? How would the K be related to this one? The new K would be equal to the inverse of that K, right? Because it's this one on top, this one on the bottom. Now it's this one on top and this one on the bottom. So you just flipped it. That's it. And like any equation, if you know all of the values except for one, you can solve for it. Right? So if we have a K like this, divided by that, and say you know this one already, and you know this one at equilibrium, you can solve for that one. It's like any equation. If there's only one unknown, you can solve for it. If the equilibrium lies to the right, the value of K is very large. If it lies to the left, the K should be very small. No question? All right. All right, so that's our equilibrium discussion, and I think that's enough information that we can now start talking about acids and bases. Back to chapter 16. All right. Concepts. What did early chemists think of acids and bases? Okay. Arrhenius, I don't remember where Arrhenius was from. I think Arrhenius was Swedish or Danish, one of those one of those two. Arrhenius proposed that acids always produced hydrogen ions from their molecules. That is, the molecule has to have a hydrogen that it can donate, that it can give up. And bases have to have hydroxyls that they can give up. So an example of an acid for this one would be hydrochloric acid in aqueous solution. An example of a base, according to Arrhenius, would be something like sodium hydroxide, like Drano, except in solution. So you can see from here that this can donate a proton and this can give up a hydroxyl. Right? So those fit Arrhenius's definition. The problem is, it didn't take long for scientists to realize that you could produce basic solutions using molecules dissolved in water that did not have hydroxyl in their makeup. Right? Perfect example, ammonia, or ammonia gas dissolved in water produces a basic solution, but there's no hydroxyl there. Right? So how do we explain that? Well, two chemists independently came up with a solution. They realized that acids and bases were only acquired that characteristic when they were dissolved in water. So they reasoned that water was a reactant in the process. So if you take ammonia and react it with water, what do you get? Well, what they said was, if we're going to end up with a hydroxyl, I mean, we're trying to stay true to Arrhenius' definition, a hydroxyl must be produced to be basic. Then how are you going to get a hydroxyl out of this reaction? Well, if you remove one of these hydrogens from water, what's left over is OH. So where did that proton go? Well, it went over here and attached itself to ammonia. So by their definition, you don't produce a hydroxyl from the molecule, you produce it from the reaction. So they modified the definition for acids and bases to say that an acid, according to Lowry and Bronsted, was a proton donor. Anything that can donate a proton. And a base was a proton acceptor. Okay? So they just threw the hydroxyl out altogether. Hydroxyl, okay, maybe you got them, maybe you don't. All we care about is the proton. So anything that donates a proton is an acid, anything that accepts a proton is a base. And that's the definition that I rely on most nowadays, particularly with living systems. There were later definitions for acids and bases. A Lewis acid or a Lewis base was actually proposed by G.M. Lewis to accommodate acid and base reactions in non-aqueous media. But we're not going to have to deal with those. So we're going to deal with Lowry and Bronsted. These are the guys that give us the definition we're going to be using for acids and bases. So there's an example. Hydrochloric acid donates a proton to water, and that gives you chloride ion plus this ion right here. So what is that ion? Picked up a proton by reacting with Right? So this one, this is the donator. That's the acid. So that makes water the base. Right? The base accepted the proton and produced this one, which is hydronium. That's the hydronium ion. And this, of course, is just the chloride ion in solution. Okay? So remember I said reactions can go forwards and backwards? What if this reaction goes backwards? Now what's your acid? That becomes the acid because it donates a proton to the chloride. Okay? But so that we don't get them confused, if we write the reaction this way, that's the acid, that's the base. This is the conjugate acid of that base. And this is the conjugate base of that acid. Okay? Just definitions. Okay, so here's a generic acid in water. And many times we write it this way so that we focus on the proton, and then A is just whatever else is left over. It could be anything. And there's the conjugate acid of this base. There's the conjugate base of this acid. Okay. So this is the author's idea of showing you what happens during a reaction. You transfer a proton from one place to the other. A good lesson to take from this illustration is that we may write protons as independently floating around in solution, but protons never occur as independent protons in solution. So when we write something like this, right, and they're all in solution, this is merely for convenience. What actually happens is that proton is transferred to a water molecule, right? But this is often convenient to write it that way. I just want you to recognize that that's not reality. Reality is transferring that proton to water, which gives you the hydronium ion. Because protons never exist independently. They're always attached to something. But you will see it written this way for convenience. And for calculation purposes, it works just as well as hydronium. Okay. So how do we tell, if I just give you a list of molecules, pairs of molecules, can you tell which one represents an acid conjugate base pair? It's really simple. A conjugate acid base pair, you start with your acid, for example, and you lose one proton. So if we put this one together with this one, that's a conjugate acid base pair. This is the acid, that's the conjugate base. If we had, let's say, sulfuric acid, like that, what happens, and this, by the way, is a diprotic acid, or sometimes we call them polyprotic acid, because they've got more than one proton available. So what happens when this reacts with water? You transfer one proton at a time. You never transfer more than one. So if we transfer one proton, that gives us the hydronium ion plus what's left over, HSO4. Right? Because when that proton left this, it left an electron behind. Right? Plus, if you put those two together, they balance. So the acid-base pair in this one is that and this. They have to have the same, non-proton part of the molecule on both sides. Plus, you can only have one proton that has left the acid. We can take this one right here and react it with water and produce another hydronium plus this one. Okay? So you have a series of reactions. We lost one proton here, we lost the second one here. Each one of those has an equilibrium expression. And the acid-base pair for this one would be that HSO4 minus and SO4 2 minus. That's an acid-base pair, that's an acid-base pair. If you see a question on a test and it asks you something like, is this an acid-base pair? A conjugate acid-base pair. Your answer should be no. Because you lost two protons to go from here to here. That is not the conjugate base of this acid. That is the conjugate base of that acid. That is the conjugate base of this acid. Okay? I'm hammering that hard because it's easy to make that mistake. A conjugate acid-base pair has only one difference. One proton. One proton lost between acid and base. Okay, so here, for example, there's your false one right there. How about this one? How many protons do we have to lose to go from here to here? We had to lose two protons, right, to go from there to here. And here, you don't even have the same, those molecules have no relationship to each other whatsoever. Because that's a chloride and that's a nitrate. Right, so we throw that one out. Throw that one out for two protons. Throw this one out for two protons. This one is the acid-base pair. We lost one proton in the process. Okay? Now let's talk about acid strength. Your intuition is going to tell you that a strong acid is anything that'll eat your hand off. Well, it's true in some respects, but that, chemically speaking, that is not a strong acid. That definition does not fit. A strong acid is any acid that we believe to be completely dissociated in water, making the hydronium plus chloride. So for this reaction, that is virtually non-existent. It all goes that way. That is a strong acid. 100% dissociation. There are several of them. Hydrochloric acid, nitric acid, sulfuric acid for the first proton. Let's see, perchloric acid. That is that's not just a strong acid, but it's also a strong oxidizer, so it's more dangerous than any of these others. But the strength of an acid is dependent upon one thing: how much does it dissociate? completely ionized in water. Right? A weak acid, on the other hand, is one that's only partially associated in water. We looked at one of those just a minute ago. Acetic acid. Right? Producing the acetate ion. Which way does this equilibrium lie? Mostly over here. We get just a little bit over here. That's a weak acid, right? So let's go back to the K expression, right? Our expression here would be hydronium, acetate, divided by the undissociated acid. Okay? So now, knowing that this is a weak acid, K is going to be a very small value, much less than 1, because these values are small, and this value is large. So the K is going to be a small value. Small K values indicate weak acid. Strong acids, actually strong acids, K means nothing, because if this were a strong acid, you get everything over here and nothing over there. So what is the quotient of a number divided by 0? Anybody remember? When you divide a number by 0, what do you get? Infinity, right? You don't have a number for a strong acid. Only the weak acids have K values for that reason. Okay. So there's our weak acid. Most everything remains as the intact, undissociated acid molecule. That's a weak acid. This is the author's idea of explaining what's going on. You can look at it in the book. Now, you might ask yourself, all right, well, with a weak acid will produce protons plus the conjugate base. So are there any situations under which this could be hazardous? Even a weak acid could be hazardous, right? All you need is enough concentration of those protons and it can eat your hand off, right? So even with a weak acid, if it's concentrated enough, then it's dangerous. And acetic acid is a perfect example. You can buy acetic acid 100%. It's called glacial acetic acid. Glacial acetic acid is hazardous. Even though it's a weak acid, at that concentration, it produces a significant number of protons that will do damage to your hand if you submerge it in that stuff. Okay? So just because it's a weak acid doesn't mean it's not hazardous. It's only not hazardous if the concentration is low. Okay. Let's see, where are we going with this one? Acid strength, right? Okay. So a strong acid, forward reaction predominates. I think this is just giving you the same thing over again. A weak acid, the reverse reaction predominates. In other words, you produce very little of protons and the conjugate base, and mostly the undissociated acid. These are some common strong acids. I just showed you some. sulfuric, hydrochloric, nitric, perchloric. Those are the best known. I used to use perchloric to digest plant material. Concentrate, you can get it, well, I use it at 70%, but you can get it higher than that. The only thing about perchloric acid is it's not just a strong acid, it's also a strong oxidizer. So if you put perchloric acid together with, say, butter and add heat, you get an explosion. Okay. So you just dump a pat of butter and some perchloric acid, put it on a hot plate, turn it up high, pull the sash down, and evacuate the building, because it will blow. So the way we made it safe was we used nitric first on our plant material. Let it sit overnight. Then you can add perchloric acid to the mixture, heat it up, no hazard. This is called pre-digestion. Okay. So we went through, and in an earlier chapter, we went through naming acids. And this is just a reminder. If you have oxygen in the molecule, you never say hydro first, right? Remember that. So you just take the ion, the nitrate ion, H's become X, it's nitrate becomes nitric acid. However, no oxygen for HCl, you do say hydro. So it's hydrochloric acid. How about this one, just as a test? That has no oxygen in it, right? So what is this ion? That's the cyanide ion. So it's hydrocyanic acid. If it's in water. If it's in water. If it's not in water, what do we call it? Hydrogen cyanide. Okay, that would be the gas. If you breathe the gas, you'll die. If you drink the liquid, you'll die. So don't do either one. All right, this is just a reminder of nomenclature. Now, an oxy acid is any acid that has oxygen in it. And for our purposes, all of those that have oxygen in them are derived from polyatomic ions, like the sulfate ion, like the borate ion, like the nitrate ion, like the phosphate ion. Those are based upon polyatomics with oxygen in them. Those are oxy acids. Organic acids are derived from those that have a carbon backbone. Organic compounds are derived from carbon. Right? So this would be the start of acetic acid. You have two carbons. This carbon has hydrogens on it. This carbon has an oxygen and a hydroxyl on it. Right? So if you look at the way we wrote it before, C2H3O2, our hydrogen. We have two carbons. We have four hydrogens, 1, 2, 3, 4. We have two oxygens. So that is acetic acid. But it's an organic acid because it has this carbon backbone. Now, just for argument's sake, which one of those hydrogens is the acidic one? Right. Which one is the one that is dissociated? None of these. It's that one right there. That's why when this one leaves, you have that one negative charge on that oxygen. And sometimes you'll see this written like that. That's the same thing. It's just written differently. And it gives you some indication about the structure of the molecule, right? You have this group here, then you have this group here. That's why this one is called carboxylic acid, because this is the carboxyl group. And that's common for organic molecules. Lots of organic molecules floating around in your body have this group on them. It's not the only one. Everybody knows lactic acid, right? If you exercise a lot, next day your muscles are going to ache because of that one right there. Formic acid, everybody's been bitten by fire ants. You ever been bitten by a fire ant? That's what he spits in the hole that he makes with his jaws. Well, that's part of it. There are some other things that go in there too that accentuate the pain. Uric acid. Anybody who has gout will collect uric acid in their joints. Citric acid, right? If you like lemons, limes, oranges, that's where most of the acidic, that's where the sour taste comes from. It's not the only acid in citrus fruits, but it's one of them, one of the major ones. It's also a central molecule in many metabolic pathways in the body. Okay, so now how do we express acid strength? Well, usually in molarity. So if you have a strong acid and you're told that the acid is 1 molar in concentration, then you know that it's going to completely dissociate here. So if you know this is 1 molar, that's 1 molar, right? Because all of this goes to that. So once you know that, you can express the acidity of that solution in terms of the molarity of the hydrogen ions. So we would say this equals 1 molar. Okay? What else do we know? Well, we know that for conjugate acids and bases, they are the converse of one another in terms of strength. So remember what we said a base was. According to Bronsted and Lowry, a base is a proton acceptor. So this would be a base conjugate of that acid. It would be a proton acceptor. All right, so if this is the conjugate base, and this is the acid, if the acid is strong, the base is weak. So what do we mean by that? Well, we know what strong acid means. It dissociates completely. But when we say a weak base, it attracts protons. It accepts protons very weakly. In other words, it doesn't want protons. So if this is strong, that's weak. If we have acetic acid, going to that plus this, if this is weak, what kind of conjugate base do we have? That's a strong base. It has a strong attraction to protons, right? So if you have a weak acid, the conjugate base is strong and vice versa. So what does that mean for this arrangement? Strongest to weakest base. Well, we just said that this is from a strong acid, so it's a weak base. So that's going to be the weakest.
Hey, Dr. Block, can you hear me?
Yes.
Is there any way I can adjust my settings on here? Because like everything, like I see you, but everything's a little fuzzy and I really can't make everything out.
I can't do anything on this end. I've got a 4K camera here, so it's picking everything up.
Do you know if there's anything I can do on my end?
Not right offhand. To
Okay.
make it look better,
Yeah.
it could be the signal. You don't have a good signal, or it could be your computer.
Okay. But you'll be putting this up on YouTube anyway, right?
Oh yeah. Oh yeah.
Okay. I'm going to leave it, and then I'm going to join back and see if it'll work out.
Okay, you're gonna reboot your computer.
Yeah.
Okay.
Okay.
All right. So this is the weakest base. Which one's the strongest base? Well, if we come from a weak acid, then this should be a very strong base. So that should be the strongest base, and then water's in between. All right, so that should be the order. And there's the logic that led me to this point that I just described here. It's on the slide. Any questions so far? Probably didn't think acids and bases could be this complicated, did you? Well, leave it to chemists to do that. Let's see. I don't see anybody new. Still missing one student. Okay, acetic acid and hydrocyanic acid are both weak acids, which means they will produce strong conjugate bases. But which one produces the strongest conjugate base? Acetic acid is stronger acid than HCN. So if acetic acid is a stronger acid than this one, what about their bases? Well, the conjugate base for this one is that, and the conjugate base for this one is that. So how about their strengths? They're just the opposite. If that's stronger acid than this, that's a stronger base than this. Okay? Oh, now they want us to put these in order. All right. So we know that the weakest base is this one because it comes from the strongest acid. And we know that the strongest base is this one because it's stronger than that one. So that's the strongest base. This is the next one. And then water's in the middle. All right. Now, here's another item that we need. You see how we're doing on time? 9:05, and we go till what, 9:40? Okay. I hope I can get finished. If not, it will be on YouTube. There's an interesting thing that happens to water. If you have pure water, nothing else, you'll find that when two water molecules approach one another, one of them acts like an acid and one of them acts like a base. So if this is the base, the proton transfers to that one and leaves behind that one. So this is the conjugate acid of that base, and this is the conjugate base of that acid. Okay? Let's see, I want to be sure I know where I'm going with this. Okay. This has got a special name. The water in this case is called amphiprotic. That is, amphi means both ways. It can go either way. It can either give up a proton or accept a proton. But this does happen in water. If there's nothing else in there, you will get this reaction. It won't produce much of it, just a very little bit of that, but it does happen. And we can write an equilibrium expression for this reaction. This is aqueous, this is aqueous. Okay, so what would the equilibrium expression be? Initially, we would write this, and we put a KW down here for water. So that one times this one, right? Products divided by reactants. But something I didn't tell you before that I should have. When we write an equilibrium expression, if there's anything in there that does not change, we strike it out. That includes pure liquids. It includes solids. Well, those two, pure liquids and solids, don't count. Right? So our expression for water is simply the hydronium ion concentration times the hydroxyl ion concentration. Okay? That's our equilibrium expression for water reacting with itself. And that KW at 25 degrees centigrade, which is standard temperature, is 1 times 10 to the minus 14. Right? So, like I said, it's a very small number. Right? 10 to the minus 14. So most of pure water is still liquid. Okay. We did that one already. Another name for this is amphoteric. Either one. Behave as an acid or a base. Okay, so what does this tell us? If the K value is this number, then where did these come from? Well, they came from the same source, right? 1 to 1. So that means that if this is 10 to the minus 14, these have to be exactly equal. Right? That's the only way that reaction can occur. For these concentrations to come from this source, they have to be equal. So in pure water, the concentration of hydroniums is 10 to the minus 7 and hydroxyls is 10 to the minus 7. This is known as neutral. Right? No acids, no bases present. But if we add some acid to that, we're going to bias this equation in favor of the acid, right? So if we add a little bit of acid to that, what's it going to do? Remember Le Chatelier? Add a little bit of acid, it's going to go back this way. But is it going to use all the acid up? Nope. There'll be some left until we reestablish equilibrium. So you will still have an acid in solution. Now, if the acid is strong, this reaction virtually becomes irrelevant because we're going to put so much hydrogen ion in there that this reaction, while it still occurs, is not significant. So that's why when you talk about a strong acid, strong base calculation, you don't have to consider this. That's a neutral solution. So if the hydrogen ions are greater than the hydroxyls, we have an acidic solution, and vice versa, we have a basic solution. Right? But whatever we put in solution still has to obey this equation. I say it's irrelevant, not really irrelevant, because when we put acid in here, once we know the acid concentration, we can calculate the hydroxyls, right? We know that one, we know this one, we can calculate that one. That reaction still occurs, and it's useful. So which of these is correct? An acidic aqueous solution is what? Hydrogen ion concentration is less than that. For an acidic solution, no. Acidic solution, it has to be greater than that value. Hydrogen ions less than hydroxyls, that would be basic. This is greater than 10 to the minus 7, that's basic. That would be basic, this would be acidic. That's the only one that says acidic. Okay, so let's use this equilibrium expression to do a couple of calculations. If we have an aqueous solution, then we know the equilibrium concentration of hydroxyls is 2 times 10 to the minus 10. How do we find out the hydrogen ion concentration? 1 times 10 to the minus 14 is equal to the hydrogen ion concentration times the hydroxyl concentration. Right? So we just solve for this one, divide this one by that one. So this would be 1 times 10 to the minus 14 divided by 2 times 10 to the minus 10 is equal to this one. So what would that be? This is a half right here. And this, if we bring this one into the numerator, it becomes positive. So minus 14 and plus 10 is minus 4. And then we convert that to scientific notation, 5 times 10 to the minus 3 molar. I did something wrong, didn't I? I went the wrong direction. Right. I moved this one that way, so this one had to get smaller. 5 times 10 to the minus 5. So what does that mean? Is it acidic or basic? Well, if this is the hydrogen ion concentration, right? Hold on a second. Is that right? Yeah, it's the right number. Okay, so this number is greater than 10 to the minus 7. It should be acidic, right? There we go. So that is acidic. Even though you were given a concentration for hydroxyl, that doesn't automatically mean it's basic. Now, molarity calculations like this are valid, but they're difficult to work with. Right? Scientific notation is useful, but it's still a little more difficult than we want to deal with. So there was a Swedish chemist who was working with living systems primarily, and he was sick of using scientific notation. He said, I need something that's quicker, easier, takes up less room. And he came up with this expression. He called it pH. So this P goes in front of the hydrogen ion concentration symbol. And he said, I'm going to take the log of hydrogen ion concentrations, the common log. So this is base 10, right? So what would happen if he took the log of 1 times 10 to the minus 7? for hydrogen ion concentration. Right? Well, if you take the log of that, what do you get? Well, remember how logs work. The log of x equals y means 10 to the y equals x. So if we take the log of this value, we're saying the log of 1 plus the log of 10 to the minus 7, right? That's the way logs work. Once you take the log of a product, you get a summation. So what's the log of 1? 0. 10 to the 0 power is 1. Right? Just like 10 to the 0 power is 1 here. What's log of 10 to the minus 7? Well, 10 to what equals 10 to the minus 7? Minus 7, right? Minus 7. He didn't like negative numbers either. So he said, okay, we'll just stick a negative sign out there. So now that makes this one plus 7. So if this is neutral, the pH value for neutral is 7. That's where neutral comes from. pH 7 is neutral because of this transformation. And it's simply a mathematical transformation of hydrogen ion concentrations, right? So I'll give you a little heads up. You can do this transformation to any concentration. We could do it to OH. Negative log of OH concentration, right? So neutral would be 7 again. POH is 7, pH is 7 at neutral. You can also do it for entire calculations, right? We have a Ka equals something. We can have a pKa. That's just the negative log of Ka. Okay? There's nothing magical about that. It's just a log transformation. So, notice something else. There she is. Are you doing all right? Can you hear me? Brianna? Can't hear me. You can hear me. I don't hear you. I have to mark you present, though. This is a majority Zoom class today. Okay. So notice what would be an increase in hydrogen ion concentration for the scientific notation expression. We would go 10 to the minus 6th would be more than that one, wouldn't it? 10 to the minus 5th, 10 to the minus 4th. We'll be getting more and more and more. So what would happen to the log transformation? Well, more acidic is 6, 5, 4, 3. So the smaller the number of pH, the more acidic the solution. Okay? That's why our pH scale is set up like this. pH 7 is neutral. More acidic is 6, 5, 4, 3, 2, 1. So this is acidic side. 8, 9, 10, 11, 12, 13, 14. And this is the basic side. So the higher the pH value, the more basic, the lower the pH, the more acidic. And it's simply an artifact of the log transformation process. So what do we do with significant figures? Well, since it's a log transformation, you just have to take my word for this one. if we were to transform something like, I don't know, 3.654 times 10 to the minus 7, right? How many significant figures would be in your answer? The number of significant figures in your answer, pH, would be 3, the number of decimal places. Okay? So it doesn't matter how many you start off with here. What it matters is how many decimal places were in the original number before the transformation. So while we're here, what if you're given the pH and the question is, what's the hydrogen ion concentration in molarity? You just reverse the process, right? If you've got a number here, well, that's the log transformation. If you've got a number minus the log of the hydrogen ion concentration equals a value, then you take the transformation, and you got to get rid of that negative first. So you take the log like that equals a negative x, okay? Then you say 10 to the x equals the hydrogen ion concentrations. So 10 to the minus x equals the hydrogen ion concentration. So for your calculators, if you're given a pH value, you just take the negative of it, and then on your calculator, you find the key that says 10 to the x power. And that's how you apply this to give you the hydrogen ion concentration. It's called the anti-log, but on your calculators, it's 10 to the x. And it's usually a function key above your log key. Okay, there's our pH range. I showed you that one here already. And these are some things that are acidic. Like vinegar is about pH 3. Stomach acid is between 2 and 1, depending on the meal. Now, if you eat an Italian meal, your pH will probably drop down toward 1. If you eat a complete vegetable meal, it'll stay up around 2 or a little higher. All right, so let me see. I'm trying not to run out of time before I make all the points I want to. Okay, we'll do one of these calculations, and then we'll get over to buffers so we don't run out of time. Because as far as living systems go, the most important concept out of this whole chapter is buffers. So we're going to get to buffers pretty quick. But first, let's calculate the pH for this one. 10 to the minus 4 molar hydrogen ion concentration. So we take the negative log of that, right? So what's the negative log of that one? Well, the log of it is just minus 4. And the negative gives us plus 4. That's pH. That one's easy because that's a 1. That's not a 1. Then you've got to punch it in your calculator to find out what it is. Before we had calculators, we had to look it up on log charts, log tables. That was loads of fun. Okay, there's the calculation. Values for it. So here's a 0.04 molar hydroxide. 0.040 molar hydroxide. Okay, so how do we do that one? Well, one way is we can put it in the expression of that times that equals 1 times 10 to the minus 14. Right, and that'll give us the hydrogen ion concentration. Then we take the negative log of that and gives us that value. And that's probably the way this one is done. Yeah, that's the way we did that So the pH for this one becomes 12.6. All right, but I've got a neater way to do it. And I'll show you right now. Remember we said Kw equals hydrogen ion times hydroxyl ion. Okay? So let's take the negative log of that entire expression. That's valid. We can do that. It's just a mathematical manipulation. So the negative log of this whole thing gives you what? Well, the negative log of Kw is PKW. The negative log of this one is pH, and since they're the product, this becomes plus, and this is POH. Okay? Well, no, you don't put the sign there. Excuse me. pH, POH, add those together, you get this one. So it'd be nice to know what pKw is for water. Right? 1 times 10 to the minus 14, negative log of that is equal to 14. So 14 equals pH plus POH. So this other problem, what we could have done was we take 4 times 10 to the minus 2 and take the negative log of that one. That would give us POH, right? So if we do that, 4 exponent 2, change the sign, and then take the log. Where is it? There it is. And change the sign. So this is 1.40 rounded off. Then if we put 1.40 here, that means that 14 minus 1.40 equals 12.6 pH. Okay, so that's another way to do it. I think it's quicker. It's easier to make mistakes when you start messing around with. Oh, okay. I'll just keep talking because I've got an audience here on Zoom.
Yeah, I'll finish watching this.
Okay. So here's another example, and this is the Antilog conversion, right? We want to find out what the hydrogen ion concentration is, but we know the pH is 5.85. So we change the sign of 5.85 to negative and use our 10 to the X button on our calculator, and that gives us this value for the concentration of hydrogen ions. And here's the derivation that I just went through on the board. Right. And here's there's the examples of how to do it, right? It works great, no problem. Right. There are other examples. So the hydrogen ion concentration for a strong acid is actually the same as the concentration of the acid that's given. So if we say the acid is 2 molar hydrochloric acid, the hydrogen ion concentration is going to be 2 molar because of complete dissociation. And then the pH, there's nothing magical about pH. It's simply a log transformation. So we can take the pH of 2 molar, and the pH is a negative sign in this case. Now, that's not very useful, actually, but it's just a demonstration that it can be done. Sorensen himself would never have used pH for something that is that concentrated. You know, 1 molar concentration will be I have to be honest with you, I don't know. Let's see.
1 molar, negative log. So it'd be 10 to what equals 1? Oh, 10 to the 0. Right, so pH of a 1 molar solution is equal to 0.
Most of the things that Sorensen was working with, he would have kept his pH values between 2 and 12. Okay, so here's an aqueous solution of hydrochloric acid. Now, once you get down into lower concentrations, even strong acids, the pH calculation is valid, and the pH is 2.7 in this case. And then to calculate the hydroxyl of the POH, you just subtract it from 14. So in this case, this requires some logic. So if you're given a pH of 1.5 times 10 to the minus 11 solution of hydrochloric acid, first you have to ask yourself, what's the dominant reaction? The dominant reaction in this case, because that concentration is so low, is actually less than the dominant concentration of water at 10 to the minus 7, right? So the water dissociation is the dominant reaction. And this reaction means absolutely nothing to the overall pH. That concentration of hydrochloric acid, if you add it to water, is going to produce a pH of 7. Now for nitric, right, at that concentration, yeah, it's a lot higher concentration than the hydrogen ion concentration for pure water. So we are valid, our calculations are valid, producing a pH of 1.82 for a strong acid. Now, buffered solutions. What is a buffered solution? You can hear buffers thrown around in reference to almost everything. You can even have a buffered computer program. But in chemistry, a buffer means something very specific. A buffer solution is any solution that resists a change in pH. I didn't say it freezes the pH. I says it resists the change. If you add acid or base, if you add either one to a buffered solution, the pH will change only slightly. Whereas if the solution is not buffered, say pure water, if you add acid or base to it, the pH will go shoot one way or the other. So it would be useful to know how buffered solutions behave. Why do they behave the way they do? Most buffers are a weak acid combined with its conjugate base, right? So a buffer solution, a solution that's buffered with acetic acid will be a combination of this one and this one in some form. Whatever soluble form of acetate ion, we could say sodium acetate. That would work just fine. So you would combine a certain amount of this one and a certain amount of that one, and you get a buffered solution. So what happens? Let's see. Am I jumping the gun here? No, not really. So let's look at the acetic acid as an example. Oops. Plus water yields
that hydronium, and this acetate ion, right? That's the controlling reaction. Now, what happens if you add acid? Right? Where is the acid going to enter this reaction? Right here. If you add acid to that beaker of buffer, you're going to be adding this one. So what happens? Well, Le Chatelier says that if this is at equilibrium, if you add that one, and this is a strong base, right? Because this is a weak acid, that's a strong base. It has a strong attraction for protons. If you add protons, this is going to pick those protons up and send it back over here, right? So that means it removes most of the added protons, right? So if you add acid to a buffered solution and think, oh boy, I'm going to get a more acidic solution, guess again. With this buffer in there, it's going to suck those protons up, send them back over here. Okay? Now adding a base is a little trickier to understand. So what if we add a base? Well, let's say for argument's sake, we add a base in the Arrhenius model, right? It has hydroxyls, like sodium hydroxide. What is it going to do? Well, it's going to react with this one, right? Remember, when water reacts with itself, it produces a little bit of hydronium and hydroxyl, mostly over here, right? So that makes it a very, very weak acid, makes this a very strong base. So this strong base is going to pick up those protons, or take protons from this here and leave water behind, okay? So when it takes up those, as you add it, which way is the reaction going? It's going that way. Le Chatelier says it's going to go that way to reestablish equilibrium. So what has happened? Well, you added hydroxyls, but where did they go? We changed them into water. So there's no change in pH there either. Well, not much anyway. The equilibrium says there'll be some of these left over, but not many. So that's what situation where you add acid in one case, base in the other. And this reaction says that whether you add acid or base, you're not going to get a change in pH. Not a very large one. Except when you have added enough acid or base to consume all of that or all of this in the process. That's called buffer capacity. If you exceed the buffer capacity, then all bets are off. No more buffer. Okay. So we're out of time. Let me see if I need to continue discussion. This is the last slide, I think. Yeah, this is the last slide. If a solution of ammonia to which you've added ammonium chloride, what reaction will occur if a strong base such as sodium hydroxide? Well, to make a long story short, the best answer is this one. Sodium hydroxide added to that is going to react with the ammonium ion and leave sodium behind and make ammonium. You can draw that out for yourself. Just set it up like this. Ammonium will be on this side, and ammonia will be over here. Right? And the reaction is predominantly going to be over there. So then you say, what does it react with? And you can get a similar scenario, but in this case, we're working with, rather than a weak acid, we're talking about a weak base. But the reactions produce the same results, a buffered solution. Okay, that's it. So this is
Tuesday, Thursday, we'll have a review. So do some homework problems, look at that review document, and come to class with some questions. Hopefully we won't be snowed out. Any parting comments before I shut it down? Nope. Okay. We'll see you in a couple of days.